Hey, Alicia.
Hi, how are you?
How are you? How are you? I'm doing fine.
I'm doing pretty good. I got
That's
my
good.
scores back for OChem.
Oh, the midterm exam. How did you do? Are you happy with your score?
Um, I am. It's much
Uh-huh.
better than Gen Chem, so
It's much better than Gen Chem. That's so good.
yeah.
What was the average for Way's class? The average for Farhat's class in 118A was 75. But
Yeah,
for
I
his 118C
heard.
is 59. Uh-huh.
For Wei, she didn't discuss average, so
Oh, she doesn't discuss
yeah, I don't really know.
average.
Yeah, sadly, no.
Oh, shoot. Does she give a normal grading scale, like a grade cutoff, like what is an A, what is a B, what is a C?
No, she doesn't do cutoffs. It's just like out of 100. So whatever you get from that, and no curve on the midterms, but we get a curve on the final exam.
I see. I see. That's
Yeah.
good. That's good. Yeah.
Um, I did have a few questions. This is like regarding the homework.
Yeah.
Some of these concepts I don't really understand, but I kind of, if you want, I could either screen
Yeah.
share or screenshot it. Which
You
one
could
would you prefer?
share,
Okay.
and then
Let me
I can
see.
annotate on.
Okay.
Recording in progress.
Mm, trying to see how I can do it. Um,
Hey Rand, I'm gonna go over the rest of the like chapter 22 stuff soon too.
All right, take your time. Thank you so much.
Yeah. Let's see.
um, mm, are you able to see it?
Yes, I'm able to see it.
Okay.
I yeah. So you want to get started with question number 5 or number 6?
Um, I think number
Number 6.
6.
Okay. In cyclohexane, all hydrogens in adjacent carbons is staggered.
I'm thinking torsional strain, or no, 1,3-diaxial strain is what we talked about.
All hydrogens in adjacent carbons. In the cyclohexane, adjacent carbons. 1,3-diaxial strain is staggered. Minimal. Staggered. Adjacent carbons. So do they mean axial or equatorial? If it's axial, then it would be 1,3-diaxial strain. Oh, but if it's
Mm-hmm.
equatorial, then would that make them adjacent? Let's
Mm,
see. Yeah, the wording here is a little bit confusing for me.
yeah, that's why I was a bit confused.
Do you get multiple attempts for this, or is
No,
it
this
just
is just like one
one attempt?
submission. Yeah.
Oh shoot. Hmm. Um. Yeah, I'm not too sure with her wording and like style of questions for vocabulary, but I would
Mm-hmm.
guess in cyclohexane, all hydrogens in adjacent carbons is staggered. Is staggered. Minimal
I'm thinking
staggered.
torsional strain.
minimal torsional strain. Yeah, I would go with minimal torsional strain as well. Because if they're not staggered and they're eclipsed, then that's when torsional strain is introduced, right? Torsional strain is there for eclipse, but not for staggered. So I would go for torsional strain. Right.
Okay.
That minimal there is a keyword. Like I didn't see that minimal in parentheses. Minimal torsional strain. Yeah.
Well, how does saying like minimal help?
Yeah. If minimal wasn't there, then it looks like it's showing that the staggered will have torsional strain, right? The staggered groups. But the staggered groups will have less torsional strain, right? Because they are away from each other. They're not touching each other. They're not eclipsing each other. So
Okay.
they don't have torsional strain. Right.
Okay, that makes sense. And then this is in substituted cyclohexane, like conformers more stable. Is this like just like on the general idea of like axial and equatorial, like basically what you discussed from last time?
Yes, axial equatorial is more, which means wait, can I see the options again? Yeah, like what we discussed last time. Like so this one here is, think of it as the bulky group, right? Like where do you want the bulky group to be at? The axial or equatorial position to be more stable?
I think it's
To
equatorial, right?
Yep, equatorial. To
Okay.
reduce what kind of strain or reduce what kind of
A 1-3?
thing. 1/3 the axial strain, right? And that would make it more
Okay.
stable, lower energy, which means the larger group should be put in the
Oh
equatorial
wait.
position.
Okay.
Wait, what is that? What, axial conformer, equatorial conformer of chair? Wait. I have never seen that before. Axial conformer of chair flip. And then hindrance, it should be HINDRANCE. I also misspelled hindrance as hindrance before, so I'm also making a mistake too, but it should be no E there.
Yeah.
The axial conformer of a chair flip is the conformation in which the groups are straight up and down. In a chair flip, all axial groups are converted to equatorial groups and blah blah blah. What does she mean by axial conformer and equatorial conformer? Equatorial conformer. In chairs. In the cyclohexane and chair conformation, the equatorial group. So axial and equatorial is just what we use to refer to groups, like where they are at. Right? Like the flips are like, I don't know if there's a name for them. Like, 'cause you know how there's one way that goes like like a lightning bolt, and the other way you
It's like
rotate it
up and down.
counterclockwise. Yeah, up and
Oh,
down thing. Right.
yeah.
You rotate everything counterclockwise. I don't know if there's a name for those flips. We just call them chair flips of each other. Right. So that is a little bit throwing me off too, but I would stick with equatorial because
Okay, that
equatorial is the
makes
more stable
sense.
one. Yeah.
So going on to like the next question, we haven't really talked much about amino acids and sugars, only just by a little bit.
Yeah.
So I was wondering if we could maybe try this
Mhm.
one or like maybe explaining. She did say like D and L, but she doesn't really explain
Mhm.
it too much.
Right. So amino acids and sugars, that's gonna be the end of 118C. That's interesting that she's putting it here in 118A, where amino acids, they are mostly gonna be L-amino acids, right? And D versus L-amino acids is gonna talk about like what uh, rotate, what direction they rotate light in, plane polarized light.
Okay.
So if you put like an amino acid in like some kind of test tube or something, and then you shine light through it, there's a direction in which they rotate the light, like clockwise or counterclockwise. Think of it as R or S, right? But it's not exactly RS because that's like meant rules. D and L is like the intrinsic natural thing that we can't calculate through like rules, right? So it's just an intrinsic natural thing where naturally most amino acids are L-amino acids, and that's a conceptual trivial thing that you'll see in biochem and 118C. This one was
Oh, okay.
and Chem1 So that's just a remembering thing. Like
Oh,
it's
so this is like
it's just
about polarized light?
yeah, it rotates plane polarized light to counterclockwise for L amino acids, and
Oh,
D rotates it clockwise to the right. And then D is dextrorotatory, L is levorotatory. Right. While most
okay.
sugars are G
Is
sugars, yeah. Uh-huh.
so are we like do you think we're expected to know this, or this is just like just
Usually in 1A,
already?
you don't learn this
Uh-huh.
stuff. You don't learn amino acids and sugars, but for Wei, like since she's putting it in the homework, I would know it.
Uh-huh.
I would know it.
Okay.
Yeah, yeah. And you,
So like
uh-huh.
so what's an easier way to like
You-
understand this, or like I guess
yeah. To understand this, an easier way,
mhm.
it's one of those things that we find in nature, like through experiment. Uh,
Yeah.
let's see. I'm trying to think of it conceptually why we find it in L,
Mhm.
conformer, rather than D. Yeah, I can't think of a reason why. We've just like introduced it like a fact, like biology. That's why I don't I don't like biology classes like that, because I can't understand it.
Okay.
It's just like
Yeah.
a fact thing.
Mhm.
I can't explain that.
Okay.
Yeah.
Well, I guess it's just one of those things.
Yeah.
Okay, thank you.
Mhm.
Um, and for this one,
Mm.
the one
Mhm.
mixture of positive and negative
Enantiomers.
enantiomers.
Yep, like one enantiomer will rotate direction in the clockwise or positive
Right, and
direction,
then one is
or the
counterclockwise.
negative direction. Right.
Right.
So one enantiomer itself, if you just focus on that one and ignore everything else, ignore the solution, ignore the other enantiomer, that
Mm-hmm.
is optically active if it can rotate plane polarized light, like in a direction, clockwise or counterclockwise.
Right.
Right. But enantiomers, they will rotate the same magnitude, like the same degree of light, but
Mm-hmm.
opposite direction.
Right.
Right. So one is gonna be positive 50, let's say. The other one is gonna be negative
Mm-hmm.
50. And
Right.
if placed in a solution, they combine together and they cancel out. They add up to a net rotating thing of 0. Right. So they rotate together 0. Like what
Right.
Levens uses is like I like this analogy. Imagine two people in a car driving down the woods, and then they're like fighting over the steering wheel. One guy is steering the wheel to the right, like the same strength, and then the other guy is steering the wheel to the left, like counterclockwise.
Mm-hmm.
The other way is clockwise, to the opposite direction. Um, the car is not going to go right or left because it's going to stay still, right? They add the forces add up to 0, so nothing's going to change to the wheel, making them
Oh.
optically inactive because they add up to 0. Right?
Oh, okay, one is going left and one is going right. And
Yeah, one
so
is
you're
going
not going
clockwise.
anywhere. So
Yeah,
like
right,
they
right.
cancel each other out.
Mm-hmm.
Oh, okay, that makes sense.
And that one-to-one mixture of enantiomers, right? Like if you have a one-to-one mixture of enantiomers, that's called a racemic mixture.
Racemic mixture.
Racemic mixture, yeah. Mm-hmm. So you might see that again in some other homework or problem set. Racemic
Mm-hmm.
mixture. Mm-hmm.
Okay, that makes sense. And then for this one, I'm not sure if I'm getting this right because there's no dash or wedge. So
Mm.
I'm just assuming that we're just going based on
Mm-hmm.
atomic weight.
Yeah,
Um,
so in Fischer projections, right? There is dash and wedge, but it's invisible. Like it's
right.
assumed right there. So
Okay.
the dashes are the vertical lines. All those vertical lines are dashes,
Mm-hmm.
and all the horizontal lines are wedges. And do you know what direction those bonds go to? Like, do they go towards you or away from you? Like, let's say the wedge bond.
The wedge goes towards you, and then the
Yeah.
dash is away. So like we would expect the hydrogen to be away from you, meaning
Uh-huh.
it would be in a dash.
Yep. Right. Right. That's correct. The hydrogen would be a dash going away from you. And when we assign R and S, do we want the
Mm-hmm.
lowest priority group on what direction? Like when we assign R and S.
We want the lowest priority group away from us,
Yep.
meaning that would be in wedge.
Dash.
Or, oh yeah, sorry,
Uh-huh.
dash. And if it's not, let's say it's like on the heaviest one, the heaviest atom or like group is a dash, we would want to flip it, meaning you would flip the R and S.
So that technique that you just said will work for most of the examples, but not all examples,
Okay.
right? Because the 100% like for sure way to get it right all the time is don't focus on any other group. Like don't focus on the bulkiest group. Don't focus on like the middle groups. Only focus on the lowest priority group, which is usually the hydrogen, but sometimes it's not hydrogen. Sometimes it's like methyl or something like that. And then we want that hydrogen on the backside, the dash, right? In some examples, you see that lowest priority group on a wedge, right? And then when you see that lowest priority group on a wedge, that's when you flip it, and then everything would be right, like
Right.
what you just said. But then sometimes the lowest priority group, like let's say hydrogen, is not on the dash or a wedge. This is the hardest example here. Sometimes the lowest priority group is on a flat bond, like the planar bond. And then you have to do something else. You have to like think about it more 3D, and I'll show you on notability as well, and I can draw it out for
Okay.
you. But if let's say the lowest priority group hydrogen is on a flat bond planar, and the bulky group was on the dash. When you assign RNS normally and you flip it, you could still get the wrong answer, because
Really?
we're not worried about the bulky group. Yeah, we're only worried about the lowest priority group, right? We only
Okay.
flip the RNS if the lowest priority group is a wedge, right? You can only do that trick like if the lowest priority group is a wedge, like if it's going towards you, right? The way that you were thinking about it is you were thinking about the bulky group on the backside, and then you flip it. But that's not going to be always correct, because the examples that is not going to always be correct is when the lowest priority group is on the flat bond sometimes. Okay, flat bond.
Okay.
Yeah. So just think about the lowest priority group always. If it's a wedge, flip it. If it's a dash, do everything normally. Don't have to flip anything. If it's a flat bond, you have to do some more stuff. But I'll show you that later.
Okay.
Yeah. So this one here, let's say it's 1, 2, 3 going this way. Okay, so how would you assign RNS for this chiral center here? What's your 1, 2, 3?
I think bromine would be 1,
Mm-hmm.
and then CH2, CH3, that would be 2, CH3 would be 3, H would be 4, so go R.
Yeah, it will be R. And then since the hydrogen is already on the backside, do we have to flip anything, or can we keep it as R?
We can keep it as R.
Yeah, we can keep it as R. So the structure above would be R to bromobutane.
Okay.
Yeah.
And how would we know that this is already on the backside? Is it just because it's like up, or?
Yeah, so the Fischer projection, all the vertical lines are going to be dashes, right? So it will make more clear, like more sense if I draw it out, but all the vertical lines, think of them as dashes. All the horizontal line, think of them as wedges. And when I think of Fischer projections, I think of like like a person, and the horizontal lines are like their arms reaching out for a hug, like going towards you for a hug, you know?
Oh, okay. And you said the horizontal ones are the
The horizontal ones are the
wedges.
wedge, yeah, going towards you. The vertical ones are the dashes going back.
Okay, that makes sense.
Yeah. Yeah. Let's see. The structure above has a stereo center of 1. Okay. So how would you assign RNS for that chiral center right there on carbon 2?
This one?
Yeah. Well, first, how would you number this in nomenclature? Like, what's your number 1 atom, and what's your longest chain? That's the first thing to do.
I think one,
Uh-huh.
like from the CH3,
Uh-huh.
2, 3, 4.
Right. Why wouldn't it be the other way around? Why can't that be number 1 and go in the opposite direction. 2, 3, 4.
Oh, well, I see there's a bromine and a chlorine on either side, so
Yep. On the carbon 2, like if you go either way, like 1, 2, the first
yeah.
substituent is on carbon 2, either way. So if there's a tie there, then you look for alphabetical order.
Yeah.
The
So
substituent.
bromine.
Yep, bromine. B becomes like is first before C. So that's why we number the top carbon number 1. And then we
Okay.
go down 1, 2, 3, 4. Yep. So what's the chiral center? What's the not hybridization? What's the RS for carbon 2? What's the stereocenter?
It would be this one.
Yeah. Would that be R or S?
Well, based on, well, I'll try explaining it.
Yeah. Try explaining it.
So
That's the best.
we said that the vertical line would represent dashes, and we would want the dash to be on the lowest priority, but the hydrogen has the wedge, so we would want to flip it, so we would have to keep that in mind. And then bromine is first, then the methyl, then the hydrogen, and then this carbon, right?
Or so bromine is first, and then what's second? Or what did you say? What group was second?
The methyl?
Oh, right. So when we assign priority for groups, we assign them based on atomic number, right? So if you look at the carbon right there, look at the second carbon,
This one, yeah.
right? Yeah, and look at the groups attached to it. The very first atom attached to that carbon. So we have a bromine, a hydrogen, and 2 carbons. Bromine has the highest atomic number out of all those atoms, so bromine has the number 1. But we have 2 carbons now. They have the same atomic number. There's a tie, right? The carbon on the top and the carbon on the bottom. And if there's a tie, then we see what's attached to those carbons. I can't annotate on your screen for some reason, but let's see. If you look at the top carbon right there, that top carbon is bonded to 3 other hydrogens, right? Because it's a methyl, it's bonded to 3 other hydrogens. Besides to the chiral center, if you look at the carbon below, it's bonded to a chlorine, hydrogen, and carbon, right? So who would win the war, the chlorine, carbon, and hydrogen, or the 3 hydrogens in atomic number?
It would be this one with the chlorine.
Yeah, that one.
Methyl,
Right.
and hydrogen.
The chlorine,
Okay.
carbon, hydrogen.
Okay.
So that carbon there is priority number 2.
And then the methyl is 3, and then the
Yep,
hydrogen
methyl
is
is 3.
4. So then that means that it would go in the form of, yeah, this way, clockwise.
Right.
R, but
Clockwise.
because hydrogen is in a wedge position, then we want to flip it. So it'd be S.
Yes, it looks R, but then it's actually S because the lowest priority group is on the wedge, and that's when we do the flipping thing. Don't think about the bulky group, think about the lowest group. If it's a wedge, you flip it. Yeah.
So that would be, wait, 2. Okay, I see how this goes. S, and then now they want us to look at 3.
Yep.
So 3 would be chlorine is first priority. Then I would think that the one above this part is 2.
That's right.
Then the methyl is 3 and the hydrogen is 4. But again, like the hydrogen from this one is in a wedge position. So this one's also in a wedge position. So we want to know that we have to flip it because we want the lowest priority to be in a dash position. So that means 1, 2, 3, 4. So then that's clockwise. But we would switch it to be S, so counterclockwise.
Yes.
All right.
Yeah.
Okay.
Yeah. It looks R, but it's actually S because the lowest group is on a wedge. So you would flip it. That's right. Nice.
Okay. Thank you.
Yeah. No problem.
Yeah, I'll let other people ask.
Yeah.
So, thank you so much.
No problem. I think Kathy also had Fischer projections questions, but I kind of went over that already. So I'm going to go over 118C stuff now, and then we'll go back to Fischer projections at the end if we have time.
Okay.
Yep. Okay. So let's go do some 118C. Share screen. Start. Go. Yes.
Did I stop sharing my screen? Just making sure.
Yep. You stop sharing it. I shared it here. Okay.
Okay, thank you.
Okay. So yesterday we ended off with the oxidation of substituted benzenes. Now let's talk about reduction of substituted benzene. And how many did he give you here? Give you 2 reduction reactions here. Okay. One is going to be hydrogenolysis of benzylic ethers. Hydrogenolysis of benzylic ethers. Right. This is going to reduce benzylic ethers and not any other ordinary ethers. Right. We are interested in the benzylic ether, like how we were interested in the benzylic intermediates in the last examples, like the benzylic radical, cation, anion. For example, I'll give you a simple example first, and then I'll give you a practice problem to try. If we have this ether here, and we reacted with the reagents H2PDC, this is going to do hydrogenolysis of benzylic ether. We're going to reduce this benzylic ether here, right? This is an ether because we have an ROR group, right? And this is the benzylic position because it's the carbon directly coming off of the benzene. And at that benzylic carbon right there, we have the ether. So this is considered the benzylic ether, right? To predict the product quickly, find your benzylic carbon and make a cut between that carbon and the oxygen right there, right? And in this reaction, you will always get a methyl group after you cleave that bond off, right? So if there's no other groups attached to it, this is going to be considered toluene, right? And the remaining thing, think of it as a leaving group. It's going to leave as the protonated version of that. So it's going to be HOR, right? Where the OR is whatever that ether group was, and just add H there, like that. Two here, two added there and here, right? One H, one. Benzylic carbon had 2 H's, 2 hydrogens, but now it has 3 hydrogens. It gained 1 hydrogen from the H2, and then the other hydrogen from the H2 went onto the oxygen, like that. So this could get a little bit more complicated if you have multiple ethers on a molecule, and you are only interested in the benzylic ether, right? So for example, let's say I have and I will BC, right? The first thing is associating the reactant and reagent to a reaction. So that comes practice when you see a lot of these reactants and reagents. You when you see like ether with like a benzene with H2PDC, you reducing or hydrogenolysis of benzylic ether. So now the next step is to find the benzylic carbons. This is a benzylic carbon, this is a benzylic carbon, and then from this point, we see which benzylic carbon has an ether. Right? And the only benzylic carbon that has an ether is the bottom one right here. Right? That's attached to an OR group. This benzylic ether is not attached to an OR group because there's that roadblock right there, that carbon. That reactor right there, and methyl group after we split that, and it's no longer intolerable to it, and the left as a leaving get different isopropanol like that. Okay. Now the other reduction reaction that he showed you is the Birch reduction. The mechanism of this, so I wouldn't worry about the mechanism. I'll just show you the reaction and what to think about when you predict the product. So there's 3 scenarios. Scenario when there's no G or EWG, and there's a scenario where you have an EWG present, and there's a scenario when you have ED present, and actually there's a 4th scenario, which is the hardest scenario, when you EG and EWG present. Okay. Okay. Let's start with the simplest example with no EG and EWG. The benzene right here with so and then ethanol, that's going to reduce the benzene into this 1, 2, 3, 4. 1,4-cyclohexadiene structure. Yeah, where there's an sp3 like roadblock in between the 2 alkenes right there. Right. So this is mostly just recognizing the reactant and reagent, and then knowing like what kind of product gets formed from this. And the name of the reaction helps you as well. So you could label it and name the reaction as you do more practice. The mechanism wasn't given, so we don't have to worry about that here. That's an example when there's no EDG or EWG attached to it. But there is an important intermediate that I want you to know for this mechanism, which is going to be this right here. Right. So at the so in between the double bonds, there's going to be negative charges there, right? One is going to have a full-on negative charge with a pair of electrons, and the other one is going to have a radical. That. So think about that intermediate for the next scenarios, right? Because that's very important where you put the group, where you put the alkenes at. Okay. Oh, he just gives intermediates on the multiple choice questions. Yeah. So if this shows up on the multiple choice questions, then know that this negative charges on the carbons in between the alkenes. Yep. Okay. So let's look at an example with an EG present now. Say, and in Birch reduction reagents, sodium, ammonia liquid, ethanol. We have to 2 alkenes are not conjugated to each other. They can't do resonance to each other because they're separated by sp3 carbons. And we do know that there's negative charges in between those alkenes, right? Negative charges on the sp3 carbons in the intermediate. So if that's the case, right, how do we know where to put the alkenes? Like, we could put it in this order, or we could put it in this order, or we could put it in this order, right? So I'm gonna have you guess here. I'm gonna say this is A, B, C. Make an educated guess based on the intermediate. Where do you think the negative charges are gonna be most stable at? Right? What do you think the negative charges are gonna be most stable at? What positions?
I think the negative charges are going to be most stable where you have like an allylic or benzylic position, right? What we talked about yesterday.
Yes. So the negative charge is gonna be more stable at an allylic or benzylic position. Compared to like a non-allylic or non-benzylic position. But in the intermediate right here, right, referring to the negative charges on the carbon of the intermediate. So there's no allylic or benzylic position.
Yeah.
Would an EDG or EWG stabilize this negative charge? Like, let's say we have a group here on an E or EWG on that negative charge to make it more stable.
Wouldn't an electron withdrawing group stabilize it?
Yeah, electron withdrawing group would stabilize it because it's going to withdraw those electrons and make it more stable, right? It's able to like be more delocalized. It could have more room to resonance. Whereas if you put an EDG there, that EDG is gonna donate electrons into that system, and then that's gonna like be very angry because opposite, I mean, like repel each other. Those negative charges are gonna repel each other, right? Whereas if we have an EWG, just attract. So it's gonna be. So if that's the case, then draw out that ring, and then the E normally, and then knowing that because we know that in the intermediate, the negative charges were in between those double bonds, and those negative charges are stabilized by this EWG right here, like that. Right. So it's not gonna be this, because if you think about the negative charge, those negative charge. Oh wait, no, the negative charges are not there. They're here, in between the double bonds. They are not stabilized by the EWG, so that's not going to be major. And it's not going to be this as well, because the negative charges will be here now, which are still not stabilized by the EWG. But if we look at this one, the ones in purple are like what was there before in the intermediate. Those negative charges are stabilized by the EWG, like that.
So if we had like an electron donating group, I think that's the next example.
Yeah,
But
yeah.
I'm just gonna guess ahead. So if we had an electron donating group, they would be most stable furthest away from the donator,
Yeah,
right?
right. Furthest away from the donator, the EDG. That's right. You got it. So if this is the EDG, our product is going to be like this, right? Where the negative charges are not touching the EDG at all. They want to avoid the EDG, right? So a quick way to remember this is that the sp3 carbon is going to touch the EWG. The sp2 carbon is going to touch the EDG. So the EWG is on the sp3 carbon. The EDG is on the sp2 carbon. So that's a quick way to remember it without like understanding the reason behind it, right? To predict the product. Okay. So I'm gonna give you this one last example, and I will move on to the next, where there's gonna be multiple groups, EDG and EWG. Okay. Where do you think the double bonds are gonna be that for this reduction reaction?
I think, will it be like the electron withdrawing group? Because this is reminding me of when we would do like reactions with benzene, we would have like meta director, ortho director, para director, and you would have like a list of priorities. So would the aldehyde portion do the directing?
Yeah, so that technically want to direct the negative charges because the negative towards that aldehyde, the EWG, to make it more stable, right? And they want to go away from the EDG, so they're going to avoid it. So technically, yes, this aldehyde is going to be the directing group, but you're going to notice that there is a way where we could put the double bonds that will support both scenarios that we did earlier. But I like your thinking, how you're thinking of like priority groups, like which group would direct the double bonds. Yeah, so let's stick with the aldehyde. If you choose the aldehyde to direct the group, where would the double bonds look like?
The double bonds would be, so EWG would be on sp3, so the double bonds would be on the carbons, like the carbon right above that one, the aldehyde, yeah, across like that.
Yeah. EWG is on sp3, and then you'll notice that the EDG landed on the sp2, which is perfect. It works out like that, right? Because the negative charges are stabilized by the EWG, and they are as far away as possible from the EDG, like that. So they work together. Yeah, nice. Okay. So that's oxidation reduction. Any questions on that one?
No, everything is really clear. Thank you so much.
Like the shortcut, like the tips and tricks on how to predict your products, like WG on sp3, on sp2. I have to show you the reason why first, so then like you don't rely just on that trick, you know.
Yeah, no, it's really helpful actually, because you understand the reasoning, and then if you forget it like really quickly for a second on it, you remember it quickly with like the little trick, but you also understand it.
Concepts.
Yeah.
Right. Yeah, because remember last night in office hours when I think Camilla was here asking about a lab question.
Yeah, the aldol
There was
condensation.
auto condensation. I forgot the shortcut, the fast way to predict the product. So I had to like go back to the mechanism and see what's going on to get the right answer. So it's best if you understand, but if you're short on time, then you do what you can,
Yeah.
you know.
Yeah.
But just that's good.
Yeah.
Yeah. Yeah. Okay, next, phenols. Phenols possess, I don't know. I don't have the annotated lecture. He blocked that out. Possess some EDG, electron donating group, directly attached to the benzene ring, right? I think you know this is a conceptual thing. Benzene, phenol is an alcohol attached to the benzene. This OH is considered an electron donating group, EDG. Next one, nomenclature. I think nomenclature is more of a practice. You could like read the notes and practice with nomenclature.
I think Levin's
Or we
covered nomenclature and everything.
That's good. That's good. Phenols containing the higher ranking cyclic functionality are called hydroxy. Yeah, so that's the nomenclature. Okay, this is important. This is a conceptual thing here. Yes. Okay. All right, hold on. I need to read all of this just to make sure I include everything.
That's okay.
Multiple. Yeah. Yes. Okay. So, if I give you this structure here versus this structure, what would be the stronger acid and why? this is also a 118A thing. So Kathy and Elisa, this is gonna relate to you guys as well.
Would the wait, I have to think about this. So acids.
Yeah. Stronger acids, think about the conjugate base, deprotonate it, and then see which conjugate base is more stable using Chiral. Okay. Like which negative charge is more stable.
Would so if it's more stable, it's a weaker base. So would the phenol be more acidic?
Yeah, the phenol would be more acidic because if we were to deprotonate it to get this conjugate base here, versus if we were to deprotonate the cyclohexanol to get that conjugate base, this conjugate base here is more stable because it do resonance with the benzene ring, like that. So this phenol is more acidic than the cyclohexanol because the conjugate base can do resonance, more stable. Right? Okay. Now, we're back in 118B, we learned about enols and keto-enol tautomerization. Like, let's say we have this alkene next to an alcohol right here, and then that would be called an enol, alkene next to alcohol, enol. We would always tautomerize that enol into the keto form or the ketone form, carbonyl form, like that. And the process is called keto-enol tautomerization. You might tautomer where the major product is the keto form or the carbonyl form. Right. But for phenols, right, let's say we have this phenol right here. The enol form is more stable, more preferred over the keto form. And can you think of a reason why we want to keep this form, the enol form, instead of the keto form, carbonyl form?
Would it because it's I want to say like resonance, it's you have the aromatic ring. So that's really favorable thermodynamically instead of
yeah. Aromatic ring right here. That's right. Non-aromatic makes it less stable. And we prefer to go to the side as more stable structure, which is why the phenol prefers to be the enol form over the keto form. Right. Okay. Now I'm gonna give you an acid-base ring question, and then I do have like one you can see like prior sessions coming up soon, so I'm gonna have these reactions more organized. So then we could go over the rest of the reactions some other alpha hours. But we'll end with an acid-base question and then move on. Like we finished the chapter 22 some other time.
Okay.
Yeah. So let's see. If I give you let's give you 5. Okay. Yeah. Let's see. Okay. Rank 1 and 5 is acidic.
should I just say what I think it is?
Yeah.
I think so going from left to right, I think the this isn't the right name, but like the dinitrophenol would be the most acidic.
Mhm.
And then I'm not too sure if the dibromophenol or the 2-nitrophenol would be more acidic, but it's between one of those for the second rank and then the other one go after. I think then it would be the 4-isopropyl phenol would be the second to last least acidic, and then the least acidic would be just the normal plain phenol.
Yeah. So that's good. You got the first one correct because that's the most amount of EWGs and the strongest amount of EWGs. And if we were to compare this and this one right here, the strong EWG by resonance is gonna overpower the weak EWGs. Even though there's more weak EWGs here, the strong EWG is gonna like stabilize the negative charge better because it could actually do resonance with that whole NO2 group, right? So that's why this is more acidic than this one. And then if we were to compare this one and this one right here, in our group, EDG.
Oh, so it's going to
Right.
decrease the acidity, so it'll just be the plain
Yep.
phenol and then the
Yeah.
isopropyl.
It makes it less acidic than a normal benzene ring, right? That's correct. Yeah. So those are like some ranking questions that you might see on choice as well. Yeah.
Probably.
What reactions are is he on right now? Do you remember, or do you used to go to lecture for Farhat?
To be honest, I don't go to lecture. I realized very early on that going to lecture is kind of
Yeah. But most of my like my like are skipping lecture as well. Like they haven't been attending lectures too. So
yeah. I did just final
Yeah.
exam going to lecture, use
Yeah.
and use resources, so I think I will continue to do that.
Yeah, if you go, like I think it's gonna confuse more.
Yeah, and
You're
I
gonna
want to listen.
Yeah,
So
that's good. So do you watch the recordings though?
yeah,
Or no?
I
Yeah.
watch them sometimes like before the exams. I watch them like on 2 times speed and I skip around just for like the medicinal chemistry part. Because sometimes he'll drop
Has
like
he
red.
posted practice for
Posted the practice? I don't think so, but let me check. No, he hasn't. He just posted
Okay.
anyone.
Yeah. In tomorrow's office hours, I'll have like these reactions more like planned out because right now I'm just kind of like reading through the slides right now and like making this stuff up as I go. That's why it's taking a little bit slow.
No,
Because
it's
you know how
okay.
last time I was like going over like the chapter 21, chapter 1920 review. That's because that's after like all of the sessions I had like organizing the notes. But I'll
No, I
yeah.
appreciate it. Thank you so much. Like everything you've been so helpful,
Yeah.
honestly. Like it's completely fine.
Yeah. I'm glad. Okay. Kathy, did you have a 118A projection question or RS question? Okay. Oh, check Discord. Let's see Discord. Okay. Let's finish up the session with those questions. Okay. Let me download all those. It's about RS, finding how many car centers there are. Okay. Let's see. Save. Let's see. Let's see. Okay. Speed run through this. Share screen. Okay. Okay, you figured out the IUPAC name, just the chiral centers and stereo bonds? Stereo center? Let's see. Oh, chirality center is this one. Okay. This one, you figured out the IUPAC name. That's good. Oh yeah, because I think I went over that with Elysia at the beginning. RS. This one, did you figure this one out too, Kathy?
No, I need help on that.
Okay.
And for the last one I sent you, it's what like my answers were, and it was wrong for the chiral centers.
Here?
Yeah.
Let's see. Okay, I see. So this one is
It's the
this
same one, but yeah.
Yeah. Okay. Okay. Identify all of the chiral centers in the structure. So you put A. So where's A? A. That's good. That's the chiral center. B. That's good. C. That's good. G. Good. I. Good. K. Good. L. So chiral centers, right? What's the definition of a chiral center?
4 different groups attached to it.
4 different groups attached to it, and they have to be sp3 hybridized. If you look at L right here, there's only 3 groups attached to it. The carbonyl and 2 other groups, and that's sp2.
Oh, okay. So wait,
Right.
because J is 1, right?
J, where's J? G, D, 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 J, if I J, yeah, J is a chiral center. Yeah,
Okay.
yeah, J is a chiral center. Yep. So you include J as well.
Okay, so I think it's J instead of L. And the other
L,
one?
okay. Yeah, other ones, M, yep, N, yep, O, yep, P, right here, yep, R, yep.
Okay, so I just switched the J.
Yeah, try submitting that and see if it works.
Okay.
Let me cross out L. Cross out L. Not L.
Okay, yeah, that's right.
Okay, that's good. That's good. So for the next one, a compound with 2 chirality centers, 2s, 3r, 2 bromo, 3 chlorobutane is shown. Well, this is very similar to the Fischer projection that Elysia had, or like the second carbon had a bromine, the third carbon had a chlorine, and it was a butane. Convert the given structure to the wedge. Did they give you a Fischer projection form
No, that's
of
all they
this
gave.
problem? Oh, like they didn't
No,
show
it's
any other
just that.
picture, like
Yeah, I don't understand what a
Oh, really?
stereo bond is.
stereo bond. Wait, where did it? The stereo bonds. Oh, it's dash. Right. So if you numbered it like this, I mean, if you drew it like this would be your carbon 1, carbon 2, carbon 3, carbon 4, and if we see at 2, it's an S, right? Because that's part of the name, 2S. So we can't do R and S if there's no wedge or dash. If you want, what would the bromine have to be or dash?
Wedge.
Wedge, okay, that would make the hydrogen a dash, right? Because if one is wedge, the other is a dash. So hydrogen is a dash. If we assign 1, this is 2, this is 3, 1, 2, 3, going that way.
Wait, is
It's
the
R.
highest
It
priority?
will stay R.
Is the highest priority always be wedged?
No.
So it doesn't
No.
matter which one is wedged.
Yes. Well, it does matter. It does matter which one is wedge, right? Because we want the S configuration on carbon 2.
Okay.
Right. And if you put the highest priority group on a wedge, that's going to give you an R configuration. Does that make sense? Because I assign this number 1 Does that make sense? Like why bromine is number 1 and why does carbon is number 2?
I thought you assigned the numbers
part.
based on the atomic number.
Yeah, we as atomic number. Bromine has the highest atomic number to carbon 2. That's why bromine is number 1.
Okay.
Does that make sense?
Yeah, what if like the wedge was on the the CH3?
You can do that. Better way to make is to make the hydrogen in the wedge. Hydrogen in the
Oh,
and the bromine in the dash. So it looks R, but if we look at the lowest priority group, the hydrogen, we flip it to S. So that would be 2S now.
okay.
Wait, because the way that you drew it, if you drew it like this, however, then you could put the bromine as a wedge and the hydrogen as a dash. Right? Because if you do the same thing, 1, 2, 3, it's going counterclockwise now, and it looks S, it will stay as S because the lowest priority group is on the backside.
Okay.
Right? So it doesn't matter like if it's wedge or dash, it just matters on what you want it to be, R or S. Like that's the same thing as that. Like you see, because we just flipped it upside down. Like if you have a model kit, we just flipped it upside down, and when you flip it upside down, the wedge can convert to dash and the dash converts to wedge. Right? It's the same thing.
Mm.
But the way that you drew the backbone like this, and where you put the bromine, this bromine has to be a dash. Does that make sense?
Yeah.
Okay, so now let's look at carbon 3. How would you figure out the 3?
So, it's R, right? So
Yep.
first put like H as a dash.
Okay. And that would make the chlorine a wedge.
Yeah.
Mhm.
And then the second group would be on the right, and then the third one would be the yeah.
Mhm.
And that's R.
Yep. Do we have to flip anything, or does it stay R?
No, it stays R.
It stays R, and that's good. So it's gonna stay like that,
Okay, let me try
right?
that.
But if we flipped it like this, right? If you drew the bond line like this, then the chlorine would be a dash, and the hydrogen would be a wedge in this form right here. If you drew the backbone in this form like that,
Okay, and then
right?
that
But you
you
drew it like wait, what? Sorry.
and then you would have to flip that if it was in that form.
Yeah. Yeah, you would have to flip it if it's this form because this is 1, 2, 3. It looks R, or it looks S, but we flip it to R. And why do we flip it in this case?
The hydrogen's a wedge and it's supposed to be a dash.
Yes, the lowest priority group is a wedge, but it's supposed to be a dash, right? Think about it as the lowest priority group because sometimes some molecules.
Okay.
Did that work?
Yes.
That's good. Draw a plane structure for the composing dash or solid wedge. To regrade properly include hydrogen atoms, concentrators, or asymmetric carbons. Okay, so how do you start this problem here based on what we just did? How would you start the molecule?
Make a cyclohexane ring.
And let's number 1, 2, 3, 4, 5, 6. We know there's going to be ethyl. Right now, I'm not doing wedge bonds. I'm just attaching the groups based on the name. Now let's look at carbon 1. The wedge for carbon 1.
For 1, it would be R, so first put the hydrogen as a dash.
Okay. That would make the ethyl a wedge. And what would be priority groups here?
Would the first priority be the one with the chlorine?
Yeah, because if you look at the chiral center on carbon 1, assigned by atomic number, but these carbons here, right, they have the same atomic number, so there's a tie.
Yeah.
And this is the one I was talking about Elysia earlier. It's a tie. I like to list out its soldiers in order of priority. So I'm gonna focus on this carbon first, the one I just pointed at. What atoms is this carbon attached to besides the chiral center that we're looking at?
Another carbon and hydrogen? Or 2 hydrogens?
Hydrogen, like that, right? 2 hydrogens. Now let's look at this one right here. What other atoms is carbon attached to? Ignore that one, besides the chiral center.
Another carbon and 2 hydrogens?
Yep. Now let's look at this one right here.
That one's attached to chlorine, hydrogen, and another carbon.
Carbon, but the way here is in order of atomic number. So I'm gonna put the best one at the top, chlorine, and it goes worse and worse, like carbon and hydrogen, like that.
Yeah, so that would be 1.
But chlorine, it's carbon for the other ones. So that would be 1 right there. Now there's a tie between these two right here. Right? And if there's a tie, then you do it again. You go down further. What's attached to this carbon right here? Besides the previous one.
3 hydrogens?
Yes, 3 hydrogens. 1, 2, 3. What's attached to this carbon here?
Carbon, hydrogen, hydrogen.
Carbon, hydrogen, hydrogen. What wins?
The carbon, hydrogen, hydrogen.
So that's 2. This is 3. And then if
Okay.
you were to go that way, that's R, and it will stay R because the lowest priority group is on the backside, like you said.
Yeah.
Right. So this is good. Try 2.
2 is S, so would we always start with the lowest priority as a dash?
Not always, because sometimes that would make it like R or S, like depending on what you want. So you could start it off as a dash, and then see if it gets you what you want. If it doesn't, just flip it.
Okay, yeah, we'll start the hydrogen as a dash and then chlorine, wait, no.
Chlorine as a wedge.
Yeah, chlorine as a wedge.
Mhm.
The chlorine would be 1. The one, and then at 1 it would be 2,
Yep.
and 3 would be the other one.
This way.
So that would be S, and 2 should be S.
Yep. So it's working out as we want it to be. So we don't have to flip it. We don't have to make the hydrogen a wedge. We don't have to make the chlorine a dash.
Okay.
That's good.
And the same thing, start with hydrogen as a dash.
Okay.
Have chlorine as 2. I mean 1, sorry.
Okay. Yep. This time, the outside group is not 1. Or no, this one was not also 1. The outside group was not also 1, but the chlorine is going to be 1, right?
And then at 4 it's 2.
At 4 it's 2. Yep. This is 3.
Yeah, so that would be S, right? And so then you would flip the hydrogen to be a wedge.
Yep. And that also flips the methyl to be a dash. Yeah.
Okay.
In order for us to have R. Right. So right now, this looks S, but is
R.
Yeah. Try let me write it out more clearly so you could write it in your homework. Try
Okay.
this. And then the way that I put the groups in, that's the way that the wedge and dash is gonna be, but it could be different how you number it and where you put the groups at. But make sure it gives you R and S, like based on the nomenclature.
Yeah. Okay.
It worked?
No, I'm doing it right now.
Okay. Let me know if it works. Yeah. And I hope that helped to Alicia, like when I was going over how to assign RNS and if there's a tie with you, and if they take you to your other structure based on the nomenclature, like what's the procedure for that as well?
Yeah, that helped a lot. Thank you.
Yeah, no problem. What is Joseph doing here?
Hey, Joseph.
Hi.
What are you doing here?
You just
What the heck?
yeah.
Okay, yeah, it worked. Thank you so
Work?
much.
Problem.
Yes.
Yeah. When are you guys' next quiz, Elisa and Kathy?
This Thursday.
I had one of my quizzes just today, so I guess next week.
Just today. Oh, the winter stuff.
We covered
Yeah.
more RS, but like one of them was like a cycloalkane or a cyclooctane, and we had to name it with like a bromo substituent, a methyl, and a ethyl.
Oh, I see. And with
Yeah,
RS,
so
like
I'm
we
not
just did
sure if
right
I got
here.
it right. Sorry?
Oh, it's okay. It's okay. It's a quiz. You can make it make it the midterm.
Yeah, but that one was
You
worth
get it
like 10
wrong.
points. So,
Yeah.
I
And
mean,
every point matters. Every point counts.
yeah, but do you name the like the cyclo first? If
The
it's
ring, if it's the base name, it's always the base
uh-huh.
name. It always goes at the end of the name,
Oh no.
right? Like
Ah, okay.
it always goes at the
Yeah.
end.
Yeah, because we
Was it
saw an
cyclohexane or
example in the
cyclopentane?
discussions. It was cyclooctane.
Oh, cyclooctane. Shoot. Did you put cyclooctane at the beginning of the name?
Yeah, because there was an example in the discussions manual, and it said
Uh-huh.
like cyclo something hex, cyclo hex, but I guess that wasn't the IUPAC name, so
If it's a substituent, then it could be first like cyclohexyl. Cyclohexyl, like 3 cyclohexyl, cyclooctane. Right? And that would look like this. But there has to be something, no, like 1-methyl, let's say. 1-methyl. Well, that doesn't make sense because C comes first. Let's say 1-isopropyl, right? And this is 1, 2, 3 isopropyl and 3. That's the 6-membered ring right there. So if it's a substituent, then the cyclo would be like as a substituent with the YL. The O shows that as a substituent. But if it's the base name would be at the
at the
end
end.
of the name, end of the IUPAC name.
Ooh, okay. I think whatever I wrote down got me second guessing myself because I know you normally put hex like the cyclo at the end, so the base.
Uh-huh.
But I got
Right.
yeah.
Do you remember what was exactly on the cyclooctane?
Yeah, so actually let me double check. It was yeah, so one of them was a wedge, which was like a methyl, so I guess you could start off anywhere. Yeah, that one, and then um, two spaces to the right, there was a bromine in a dash position.
Like this.
Yes.
And
And then one, two, three. Then three spaces continuing in that direction, there was a dash, and then there was a line connected to that. So I'm assuming that's like a ethyl.
ethyl. Yep, ethyl. Yeah, like this, right?
Wait, you said ethyl?
Oh no! It's ethyl. It's ethyl.
Okay.
No, ethyl. It's just ethyl.
Okay. Okay.
I'm just confirming you. You know.
Okay. Yeah. That's the structure as an
Yeah.
octane. Yeah.
Right. Okay. So I'm gonna name it, and then let me know if this is what you got. Okay. 1, 2, 3. 1, 2, 3, 4. 2, 3, 4, 5, 6, 7, 8. So we have a 1 bromo. I'm gonna alphabetical order. 6 ethyl, 3 methyl, and then the stereochemistry, the base name, cyclooctane. Stereochemistry. At 1, we have 1, 2, 3. So this looks S, but it's actually R. So it's 1R. At 2, no, that's not 1. 1, 2, 3, R, and it stays R. So it's 2R. Oh no, 3R, 3R, and then 6. Tie. This one wins. 1, 2, 3. So it looks S, but it's not S because the lowest group is on the front, so it's R, 6R. Right, and then everything else: 1 bromo, 6 ethyl, 3 methyl, cyclooctane. Cyclooctane. Is this what you got, Alicia?
No. I started from the methyl. Like
Oh,
numbering it by one because I thought I when I was counting it, you would get seven in the end. Like if you started from the bromine, right? So it'll be 1, 2, 3, 4, 5, 6, 7. But if I started from the methyl, it'll be 1, 2, 3, 4, 5, 6. So I thought I'd get the least or the smallest number going from the methyl.
Yeah, so 1, 2, 3, 1, 2, 3, 1. What do you mean by stopping at 6 and stopping at 7? Like
Like if I
full
were to
ring
count,
or
yeah, if I were to count, yeah, if I were to start from like methyl, right, it would be
methyl?
methyl, then 2, 3, 4, 5, 6. When I end off at the ethyl, that would give me 6, right?
Yep.
But let's say I start from bromine, that'd be 1, 2, 3, 4, 5, 6, 7.
Oh, it's still 6, right? Because this is 1,
Oh, okay. I was
2.
thinking of doing it the other way.
Oh yeah, because we don't go the other way. When you think about the lowest substituent, we want the lowest substituent on the first, like the lowest number. I mean, you want the first substituent on the lowest number. The reason why I went this way, counterclockwise, is because it hits the first substituent first. I didn't go this way because that's gonna hit the first substituent like later.
Later. Oh,
Right.
okay.
We want the first substituent
Yeah.
on the lowest number.
Okay,
Yeah,
that makes
first.
sense. Yeah, I think where I went wrong was
Uh-huh.
that, and
Yeah.
then I guess
Like what I was
everything from
saying at
there
the
kind of,
beginning.
yeah, that too. Everything from
Uh-huh.
there kind of messed me up.
How about RNS?
I think I got that right.
Uh-huh.
I know there. Oh wait, never mind. I think there was one S that I assigned, and I think that was from the bromine because
Right.
I think I made the mistake again to like to look at the bromo rather than the hydrogen.
Uh-huh.
Cause I yeah, I think I considered it. I know for one of them was an S. I listed as an S, not an R.
Oh, I
So that
see.
was another mistake.
Yeah. You could
Not
also
sure though.
like if you want, I could go over your quizzes, like you update it, and then I don't know, I'm not gonna share it on the office hours, but I could like go over the problems, like if you share your quiz or
Mm-hmm.
midterms on your drive, and then you could ask questions about it, and I could just like draw the problem out, so we could go over
Okay.
those mistakes too.
Yeah, they haven't like put in my quizzes for some reason, so like I can't actually see what I got.
Oh,
Apparently it seems like they put in everyone else's quizzes,
uh-huh.
so not sure.
What?
I'm gonna have to
That's
talk to my TA
crazy.
about
Yeah,
that.
yeah. Talk to you today
Yeah.
about that.
Oh, also,
Uh-huh.
what's his name? I know like I was in Gen Chem
Uh-huh.
like last quarter, but I
Yeah.
remember like I would see you in the basement.
Mm-hmm.
And
The tutoring.
there's this one dude. He's tutoring there, and I said, "Oh yeah, so like Brian helped you out like a lot, huh?" And he's like, "Oh, he was like, yeah, he I was like, yeah, he seemed pretty popular down there, like over at that table." And I was saying like how, cause I remember seeing you, and I think from the first time someone recommended me to you, you had like your own card,
Oh
and
yeah,
then
the
I'm like,
business card.
and
Yeah.
then I was like, oh my gosh, that's you, cause like I see you, and like everyone would be
Uh-huh.
like, in like the circle, yeah, that, yeah, and I remember I probably had like the same date. Yes, I saw that side, and I'm
Yeah.
like. And so I told him, I was like, oh, he's like, oh, you know him? I'm like, well, yeah, like he helped me out a little bit and for 2C, and he's like, yeah, he's like, I know. He's like, how'd you know him? I'm like, oh yeah, like I got his card, and like
Oh my God. Wait, a
then
tutor said this or a
he
2T?
tutors there now
Oh, he
for
tutored
Gen Chem,
Gen Chem.
or not, sorry, not Gen Chem, OChem.
Okay. Do you remember his
Yeah.
name or Aniket,
He
Jacob?
looked
Is he Indian, white?
yeah, Indian, I think.
Indian? Aniket. Aniket.
Yeah, but he wasn't wearing his shirt. He was wearing like PJs and like a sweatshirt.
Yeah, yeah. He goes with PJs all the time. Like that's he always goes in with PJs.
Yeah, yeah, that
Oh
was him. But he was there, so
oh my God.
yeah.
That's
Did you
crazy.
know that he was tutoring
Yeah,
there?
he told me he's tutoring for physics and OChem.
Mm-hmm.
He tutors more subjects. That's
Yeah,
crazy.
yeah, that's good though. Yeah,
Yeah.
I wish I was in OChem last quarter. Maybe I would have had like you for a quarter.
Oh yeah, in person too. Oh
Yeah,
my
but
God.
yeah, it would have been crazy.
I am visiting Davis in person at the end of the quarter to give final review sessions for 118A and 118C. I'll let you know more details about it on
Oh
like
my gosh. Okay,
yeah,
yeah.
yeah. So then
I'll be
I could
so down
meet
to
you.
say hi. Yes.
Yeah. Also, since you're like kind of like long-term tutor and consistent tutor, right? I want to gift you a hoodie. Are you what's your hoodie size?
Oh my gosh. A small.
Small? Okay, okay,
Yes. Oh my
okay.
gosh. Thank you.
Yeah, no problem, no problem. And then we'll all meet in the basement, and then I'll deliver the hoodies, and then we could take a group picture.
Yes. Okay, I'm so down. Also, I did want
Yeah.
to talk to you regarding like more sessions like in addition to this. So was there that
Hmm.
one other girl that's still like looking for a pair? If not, then that's
Oh
cool. Like
yeah.
I could still do like your rates.
Uh-huh. Right. For a group, a session 118, um, the thing. Like when was that I talked about? Was that during summer or was that this quarter?
That
I
was this
forgot.
quarter. That was like the beginning of
Oh,
this quarter when I was like, I think I reached out to you
uh-huh,
again. Like,
uh-huh.
um,
Oh yeah. She's has her own package now. Like she's not doing group anymore.
okay, that's cool. Okay, so I'll probably set my package with you. I just have to.
Yeah.
Does your availability show up on your site?
Yeah, the Calendly, that's all of my available times. Right now,
Okay,
it's
that's
all
cool.
Saturdays and Sundays because I have regular sessions on the weekdays now, so
Mm-hmm.
that's all booked. But all of my open times are on the weekends now, mostly Saturdays, Sunday mornings.
Okay, I think that would work out for me. So,
Yeah.
I'll definitely look into that more. But thank you so much.
Yeah, no problem, Alicia.
Thank you.
Yeah, thanks for letting me know that story. Like it made me so like happy and proud. Like doing all this, like it's worth it, you know.
Yeah, that literally happened today, and he's like, yeah, he came in clutch and everything. I'm like, wow. I mean,
Oh my
I tend to
goodness.
observe. I tend to
I
observe things
remember
like
tutoring
pretty
him when he was in
well.
one in
An
uh-huh.
A?
Yeah, like last year he was just one in A. Like I remember
Uh-huh.
like he was one of the consistent Tuesdays like you. Like you showed up like pretty often like him. Like he showed
Uh-huh.
up often and consistently. Oh my
Mm,
goodness. I
that's
wish you took Occam
crazy.
like when I was tutoring. Like I wish
I
I'm still
know.
there tutoring. Yeah,
I wish.
in
But hey,
person.
I'm here, so
Yeah, let's go.
yeah. So
Yeah.
thank you so
Mhm.
much. I hope you have a good rest of your night.
Yeah, you too. Good night, Alicia.
See ya.
Yeah, bye bye.
Bye.